colligative properties, and the first colligative properties is relative lowering of vapor pressure. We have uploaded a video about vapor pressure and Raoult's law also. You can go through those videos to understand in more detail what is vapor pressure and Raoult's law. Okay, let's have a look at once again. Let's say if I have a container containing water only, okay, then what happens? It has water in liquid phase. Then what happens? That the molecules of water which are present on the surface, they just absorb heat from the surrounding and go into vapor phase, okay, to form water vapors, okay. And it is a surface phenomena. Always the molecule from the surface go into vapor phase, and whenever there is a liquid, there are always some vapors present over it, okay. And then these vapors exert some pressure on the wall of the container, which is called vapor pressure of the liquid. And obviously, as we increase the temperature, more and more molecules go into vapor phase and introduce more vapor pressure. That means the vapor pressure increases with increase in temperature. Now if I add a non-volatile solute, non-volatile, that means which cannot be converted into vapor phase solute, like sugar. If I add into water and mix it, then the water will uniformly mix throughout, and then some of the fraction of the surface will be occupied by sugar molecules now, and sugar molecules are now not volatile, so that means they will not go into vapor phase. So what will happen? There would be net decrease in the number of molecules going into vapor phase, because the fraction of the surface which has been occupied by sugar is not converting into vapor. Fine. So thus, if P naught was the vapor pressure of pure liquid or solvent or water, and Ps is vapor pressure of solution, it's very obvious and it's very understandable that the vapor pressure of pure liquid was greater than the vapor pressure of solution which contains non-volatile solute, and this is called relative lowering of vapor pressure. And as per Raoult's law, this change in vapor pressure, P naught minus Ps by P naught, is called relative lowering of vapor pressure, and this is equal to mole fraction of the solute, okay. This is mole fraction of solute, or we can also write it like P naught minus Ps by P naught is equal to N2 by N1 plus N2, where N2 are number of moles of solute and N1 is number of moles of solvent. Fine. Or for a dilute solution, for a dilute solution, number of mole of solute is much less than number of mole of solvent. So from denominator we can ignore this, and when we ignore it, we get a new form, that is P naught minus Ps by P naught is equal to N2 by N1, okay. Or P naught minus Ps by P naught is equal to N2 by N1. Now N2 is given mass of solute by molar mass of solute. Similarly, N1 is number of mole of solvent, or it is equal to given mass of solvent by molar mass of solvent, okay. Let me tell you what is this. N2 is number of moles of solvent, N2 is number of moles of solute. Fine. So according to this, it becomes P naught minus PS by P naught is equal to N2 by N1 or W2 by M2 into W1 M1. Fine. So this is the formula for relative lowering of vapor pressure. Next is elevation of boiling point. Boiling point of a liquid is the temperature at which elevation of boiling point. Okay, so first of all, let's see what is boiling point. Then boiling point of a liquid is the temperature at which vapor pressure of any liquid becomes equal to atmospheric pressure, that is 1 atm. Okay, now let's understand one thing. If let's say I have a liquid which has some vapor pressure, okay, and I have to make its vapor pressure equal to 1 atm in order to boil it, and it will require some amount of heat. Now if I add a non-volatile solute, what happens? Its vapor pressure decreases, and thus now it will require greater amount of heat, larger amount of heat for the vapor pressure of liquid to become equal to atmospheric pressure. Fine. And that's why there is an elevation of boiling point whenever non-volatile solute is added, and that is given by delta TB is equal to KB into M, where M is molality of the solution, KB is molal elevation constant. Okay, fine. And you can also write it like del TB is equal to KB. Let me write it once again. Del TB, that is elevation boiling point, is equal to KB into number of moles of solute divided by weight of solvent in kg into 1000. Fine, because this is molality. Okay, and if I want to write it in terms of molar mass, in that case the number of moles is equal to W2 by M2, so del TB will be equal to KB into W2 1000 by M2 W1. Okay, similarly there is depression in freezing point. When boiling point is elevated, obviously the freezing point will go down. That means if for example water freezes at 0 degrees Celsius, when I add sugar into it, its boiling point will be somewhat lesser than 0 degrees Celsius, right? And that is called depression in freezing point. The formula is again same, Kf into M, where Kf is molar depression constant. Fine, or more accurately molar freezing point depression constant, and M is molality. So del Tf is again equal to Kf into given mass, a number of moles of solute, by weight of solvent into kg. Del Tf into Kf, given mass of solute molar mass of solute into mass of solvent into 1000. Done. Next is osmotic pressure. First of all, what is osmosis? Let's say if I take a box and in between I put a semi-permeable membrane, that means which allows only solvent molecules to pass through it and not the solute molecules. One side I have pure water, let's say water. Other side I have water plus salt, NaCl, and I have water as well as salts. Okay. Water plus salt. So as per osmosis, the solvent will flow from water, from the region of pure water toward the region of solution through semi-permeable membrane, or we can say osmosis is the flow of solvent from a dilute solution to a concentrated solution through semi-permeable membrane. Okay, and now what happens if I start increasing pressure on the side of concentrated solution? When I increase the pressure, the flow of solvent slow down, and when I keep on increasing the pressure, the rate of osmosis or flow of solvents keeps on decreasing, and then there would be a pressure at which the flow of solvent or the osmosis will stop. That pressure is called osmotic pressure. That means the pressure which is required to stop the flow of solvent. Okay, and if I further increase the pressure, okay, if the pressure is further increased beyond osmotic pressure, reverse osmosis takes place. That means now the water starts moving from the concentrated solution to the diluted solution, and this process is also used to purify water purification, reverse osmosis or RO. Fine. Now this osmotic pressure is represented by pi, and pi is equal to CRT, where C is molality, R is again the same gas constant, T is temperature in Kelvin. Fine. Okay, I hope things were clear to you. Thanks for watching. Stay tuned for more videos of organic, inorganic and physical chemistry and many more, and don't forget to subscribe.